A giant planet, roughly the size of Saturn, is orbiting a star so small it shouldn't have been able to make one at all. Every leading model of how planets form says this shouldn't be possible. The planet doesn't care. It's there, it's real, and now James Webb has confirmed it, forcing scientists to genuinely rethink how giant planets come together in the first place. Stick around because I'm about to walk you through exactly what makes this planet impossible according to current theory, what Webb found when it finally got a close look, and why astronomers are calling this a genuine challenge to decades of established science. And hit subscribe now, because this channel breaks down real space discoveries without the exaggeration, and this particular mystery is still actively being worked out. Let's start with the star itself, because that's really where the entire problem begins. TWI 6894 is a red dwarf, the most common type of star in the entire galaxy, but this one sits at the extreme low end even for that category, carrying only about 20% the mass of our Sun. Stars this small are common throughout the Milky Way, and for years, astronomers have generally assumed they simply aren't capable of forming or holding on to giant planets at all. Red dwarfs make up the overwhelming majority of stars in our galaxy, somewhere around 70 to 80% of the total stellar population, yet despite being so common, they've historically been considered poor candidates for hosting large, Jupiter or Saturn-sized planets. That reputation comes directly from how these stars form in the first place. A red dwarf's protoplanetary disk, the swirling cloud of leftover gas and dust surrounding it during its earliest stages, tends to be proportionally much smaller and less massive than the disks surrounding larger, sun-like stars, simply because the star itself started out with less material to work with overall. Less disk material generally means fewer of the heavy elements and rocky building blocks needed to construct the kind of massive core that giant planet formation, under standard theory, requires. If you're the kind of person who wants space discoveries explained clearly instead of buried in jargon, go ahead and drop a like on this video right now, because it genuinely helps this kind of content reach more people who would enjoy it. Here's why that assumption existed in the first place. The leading theory for how giant planets form is called core accretion. A rocky core gradually builds up inside the disk of gas and dust surrounding a young star, and once that core gets massive enough, its gravity starts pulling in huge amounts of surrounding gas, eventually growing into a full gas giant. The process requires a genuinely substantial amount of raw material, heavy elements, dust, and rocky debris, all available within the star's surrounding disk. Smaller stars simply don't have the mass to hold onto disks that large or that rich in material, meaning their planet-forming environment should, according to the math, run out of ingredients long before a core could ever grow big enough to start pulling in gas at the scale needed to build something like Saturn. There's a specific threshold at the heart of this problem, sometimes called the core accretion timescale. Building a rocky core large enough to trigger runaway gas accretion takes time, often several million years under standard models, and that entire process has to finish before the surrounding gas disk itself disperses, since young stars only hold onto their protoplanetary disks for a limited window before that material either gets consumed, blown away by stellar radiation, or simply dissipates into surrounding space. Around a star as small as TOI 6894, with proportionally less raw material available to build a core in the first place, standard models predict that timeline simply doesn't work. The core should form too slowly, if it forms at all, missing the narrow window before the surrounding gas disappears entirely, which is exactly why researchers were so surprised to find a fully formed gas giant sitting there regardless. TOI 6894 broke that rule anyway. Dr. Edward Bryant, an astronomer at UCL's Mullard Space Science Laboratory, led a systematic search through data from NASA's transiting exoplanet survey satellite, specifically looking for giant planets around small stars. He examined observations of more than 91,000 low-mass red dwarfs, and buried in that enormous dataset was a signal nobody expected to find: a giant planet transiting the lowest mass star ever confirmed to host one. Follow-up observations using the European Southern Observatory's Very Large Telescope confirmed the discovery was real. The planet, now designated TOI 6894b, was announced formally in a paper published in Nature Astronomy on June 4, 2025. Titled A Transiting Giant Planet in Orbit Around a 0.2 Solar Mass Host Star. The scale of that original search deserves real appreciation on its own. Sifting through data from more than 91,000 individual stars, looking specifically for the brief, subtle dimming pattern that indicates a planet passing in front of its host star, represents an enormous undertaking, one that required carefully filtering out countless false positives, instrumental artifacts, and unrelated stellar variability before a genuine candidate could even be flagged for closer study. Brian has described this work as part of a systematic program his team has carried out over several years, using both test data and ground-based follow-up observations from Chile and the UK, specifically designed to hunt for exactly this kind of rare, theoretically unlikely system. That years-long, methodical search is precisely what made finding a needle this small in a haystack this large possible in the first place. If you found this as fascinating as I did while researching it, drop a comment letting me know, because it genuinely helps me figure out what other space stories are worth covering next. The numbers behind TOI 6894b only make the puzzle more interesting. The planet's radius actually exceeds Saturn's, despite carrying only about half of Saturn's mass, making it a genuinely puffed up, low-density gas world. It sits roughly 241 light-years from Earth, and unlike most gas giants, discovered around other stars, which tend to be scorching hot Jupiters with temperatures. Soaring well over 1,000 degrees Celsius, TOI 6894b runs remarkably cold, with temperatures estimated at under 150 degrees Celsius. That combination, a genuinely massive planet, orbiting an extremely low-mass star while staying comparatively cool, doesn't fit comfortably into either of the two leading theories astronomers use to explain how giant planets typically form. Researchers have proposed two possible explanations, and neither one fits perfectly. According to Bryant, TOI 6894b could have formed through what's called an intermediate core accretion process, where a protoplanet forms and steadily accumulates gas without its core ever growing massive enough to trigger the kind of runaway gas accretion that typically builds a full-size gas giant. Alternatively, the planet could have formed through gravitational disk instability, a scenario where the disk of material surrounding a young star becomes unstable under its own gravity and collapses directly into a planet, skipping the slow, gradual core building process almost entirely. Vincent Van Allen, an astrophysicist at UCL's Mullard Space Science Laboratory and a co-author on the study, was direct about the implications, saying the fact that this particular star hosts a giant planet carries real significance for how many giant planets astronomers should now expect exist throughout the galaxy as a whole. Each of these two competing theories carries its own separate set of problems when applied specifically to TOI 6894b. The intermediate core accretion scenario would require a planet-forming core to grow just large enough to hold onto a substantial gas envelope without ever crossing into full runaway accretion. A fairly narrow, delicately balanced outcome that's difficult to achieve reliably, and one that standard models don't clearly predict happening around a star this small in the first place. The gravitational disk instability scenario, meanwhile, typically requires a disk considerably more massive than what a star carrying only 20% of the Sun's mass would normally be expected to produce, meaning even this alternative pathway runs into its own version of the same fundamental resource problem. Neither theory offers a clean, comfortable explanation, which is exactly why researchers describe the system as a genuine open question rather than a solved mystery with one theory simply winning out over the other. Andres Jordan, a researcher at the Millennium Institute of Astrophysics and professor at Adolfo Ibáñez University, who also co-authored the study, described the discovery's significance plainly, calling it a genuine new challenge for existing models of planet formation, and noting it offers an unusually interesting target for detailed follow-up. Observation: that follow-up came fast. The research team had already scheduled time on the James Webb Space Telescope to study TOI 6894b's atmosphere directly, well before the initial discovery paper was even published. Webb's observation, carried out within the following year, focused specifically on reading the planet's atmospheric chemistry, since the exact mixture of gases surrounding TOI 6894b offers real clues about which formation scenario actually produced it. Because the planet runs so much colder than most previously studied gas giants, researchers had reason to expect its atmosphere might contain chemistry rarely, if ever, seen on other exoplanets. Study co-author Amaury Triad, an astrophysicist at the University of Birmingham, specifically flagged the possibility that temperatures this low could allow Webb to detect ammonia in the planet's atmosphere, something that had never been confirmed on any exoplanet before this system came along. Here's why that specific possibility matters so much. Most gas giants, discovered around other stars, run hot, often scorching hot, since the majority of easily detectable exoplanets orbit close enough to their star to produce a strong, easily measured transit signal. That heat tends to break down or prevent the formation of certain more delicate molecules, including ammonia, which requires comparatively mild, cooler conditions to remain stable in a planet's upper atmosphere. TOI 6894b's unusually low temperature gave researchers a genuinely rare opportunity to search for that specific chemical signature in a place it might actually survive being detected. Information that could meaningfully narrow down which of the two competing formation theories actually explains how this planet came to exist in the first place. Detecting ammonia specifically would matter beyond simply confirming a new molecule on a new planet. Ammonia's presence or absence in a giant planet's atmosphere offers genuine clues about that planet's overall ratio of heavy elements to lighter gases, a ratio that differs meaningfully depending on whether a planet formed through gradual core accretion or through a more abrupt gravitational disk collapse. Finding a clear ammonia signature, or conversely finding it conspicuously absent despite temperatures cold enough to support it, would give researchers a genuinely useful data point for distinguishing between the two competing formation scenarios still on the table for TOI 68924b, rather than leaving the question purely theoretical. TOI 68924b isn't an isolated anomaly either. It joins a small but growing list of exoplanets that directly challenge standard models of planet formation, each one forcing researchers to reconsider assumptions that had, until fairly recently, seemed reasonably well settled. Around the same period, Webb also detected strong evidence for a giant planet orbiting Alpha Centauri A, the nearest Sun-like star to Earth, located just 4 light-years away, adding yet another genuinely surprising entry to the growing catalog of planets sitting in places theoretical models didn't necessarily expect to find them. Taken together, discoveries like these are gradually pushing astronomers toward a broader, more flexible picture of how and where giant planets can actually form, one considerably less restrictive than the assumptions that dominated the field for decades. This pattern extends even further once you look across the wider body of recent research. Astronomers have also identified a so-called forbidden planet, TOI 5205b, a Jupiter-sized world whose atmosphere contains fewer heavy elements than its own host star, a result that similarly contradicts standard expectations for how giant planet atmospheres should be enriched relative to the star they formed around. Separately, researchers using Webb found a carbon-rich atmosphere on a planet orbiting a millisecond pulsar, a dead star's collapsed remnant, in a system so extreme that the planet itself is likely the stripped-down remains of what was once an entirely different kind of star, slowly consumed by its pulsar companion's intense radiation and gravity over time. Each of these discoveries approaches the same broad theme from a completely different angle, but they all point toward the same underlying conclusion. Planet formation theory, built up over decades using a comparatively limited sample of known systems, is proving considerably less rigid than researchers once assumed, and the universe keeps turning up exceptions faster than theorists can comfortably explain them. It's worth being clear about what remains genuinely unresolved here, rather than treating this as a mystery already fully solved. Even with Webb's atmospheric data in hand, researchers have not definitively settled. Which formation scenario, the intermediate core accretion pathway, or the gravitational disk instability pathway, actually produced TOI 6894b? Both remain live possibilities, and untangling which one, if either correctly explains this specific planet, is exactly the kind of ongoing scientific work that makes this story worth continuing to follow, rather than a single dramatic reveal that wraps everything up neatly. Reaching a final answer will likely require more than a single round of Webb observations, too. Atmospheric spectroscopy of a planet, this distant and this faint, typically demands multiple separate observation windows, each one adding incremental precision to the measured abundance of different gases before researchers can state their conclusions with genuine statistical confidence. Given how significant the implications are for broader planet formation theory, the research team involved has strong incentive to pursue exactly that kind of follow-up, meaning TOI 6894b is likely to remain an active subject of study, with additional papers and refined conclusions expected to follow over the coming months and years as more data accumulates. That uncertainty is really the honest, accurate state of the science right now, and it's worth sitting with rather than glossing over. TOI 6894b isn't a planet scientists have found a way to explain away, folding it neatly back into existing theory. It's a planet that continues to sit right at the edge of what current models can account for, exactly the kind of object researchers describe, without exaggeration, as forcing a genuine rethink of assumptions that have shaped planetary formation theory for years. So what does all of this actually add up to? A star carrying just a fifth of our sun's mass, orbited by a planet that current formation theory says it shouldn't be able to produce at all, confirmed through a systematic search of more than 91,000 stars. Verified. With one of the world's largest ground-based telescopes, and then handed off to the most powerful space telescope ever built specifically to read its atmospheric chemistry for clues nobody has fully deciphered yet. Whatever the final answer turns out to be, TOI 6894b has already done something genuinely significant. demonstrating that the smallest, most common stars in our galaxy may be capable of building far more than researchers previously believed possible. That broader implication is really worth sitting with for a moment. Red dwarfs make up the vast majority of stars throughout the Milky Way, meaning even a small upward revision in how often these stars can host giant planets translates into a potentially enormous change in the estimated number of gas giants scattered across the entire galaxy. If a star as small as TOI 6894 can host a planet like this one, researchers have real reason to wonder how many similarly unlikely systems remain undiscovered, simply waiting for the next systematic search through the right dataset to finally reveal them. Every unresolved formation question surrounding TOI 6894b, whatever the ultimate answer turns out to be, carries implications that ripple outward considerably further than just this one system. If space discovery stories like this one, grounded in real published research from Nature Astronomy, and the scientists actually running these observations, are what you want more of, subscribe to this channel and turn on notifications, because the atmospheric data from TOI C6894b is still being analyzed. And there's a real chance the next update finally reveals which theory actually explains how this impossible planet came to exist. Thanks for watching, and I'll see you in the next one.